One of the most famous integrals in all of math looks deceptively simple, and it's called the Gaussian integral, and it appears pretty much everywhere in physics, stats, and probability theory. But the strange thing about this integral is that, unlike most functions that you might learn about in calculus, this one actually doesn't have an elementary antiderivative. So, in other words, what I'm saying is you can't integrate it using the usual rules of calculus, right? And yet, mathematicians discovered that the total area under this curve across all space is some constant, right? But why am I doing this integral? Let me just tell you about some of its common places where you may see it, right? So, for example, stats, right? In stats, it describes the normal distribution, which looks like this. And also in physics, these Gaussian curves describe how heat may spread through a material, right? So that equation looks like this. And in quantum mechanics, which is one of my favorite topics of physics, it describes the ground state of the quantum harmonic oscillator, which looks like this. And actually, the reason why this last equation, which is the quantum harmonic oscillator, is so important is because it's actually used to model atoms and even vibrations, like really tiny ones in solids, right? And actually, to find this normalization constant, you actually have to integrate psi of x. So you have to do the integral over all space of sine node of x squared dx, and it has to be equal to 1, and so that's how you find a by actually doing this integral. So you can't really normalize it without computing the integral over all space. So really what's happening here is, by understanding and really solving this integral, you're not really, solving your ordinary average calculus trick or puzzle question. um, you're also, uncovering one of these mathematical structures that would underpin much of modern physics, without really you realizing or understanding. So I'm going to begin by deleting all of this. So how do we begin, right? So what is this integral equal to? So we know that it's a definite integral, right? So let's just say it comes to some value I, right? So we're just going to say let I equal this integral. And so our next step is to use a trick from measure theory, which is from higher level university physics, more specifically Fubini's theorem, or Fubini's theorem, however you say it. And basically, what we're going to do is multiply or square both sides of the integral. So we're going to write I squared is equal to the integral from minus infinity to positive infinity of e to the minus x squared dx times the integral once again, right? But instead, the trick is this time I'm going to change and use y as my dummy variable. So they're really going to come out to the same thing. But instead, what I'm doing now is I'm just introducing y to be my dummy variable. So now what we can do is we can combine the two integrals and write it as a double integral from of e to the negative and then x squared plus y squared dx dy. And so initially, let's try to understand, kind of what's going on here by writing this double integral, right? So initially with our first integral we were really just finding the area under 1D curve, but now I've turned this simple 1D curve problem into now seemingly finding the volume underneath a two-dimensional surface, right? But one thing that is really good about this is this x squared plus y squared term, right? This is pretty much like the distance from the origin, right? So say you have, this, you could think of it a vector or a line, and basically you have an x component and you have a y component, and by Pythagoras, you know that x squared plus y squared is just r squared. And so what this kind of means is that our integral here is actually circularly symmetric, right? And so that's why this trick would kind of work. So yeah, so that's a good part about this. But the thing is now x squared plus y squared is kind of weird when we look at Cartesian coordinates, because we know that x squared plus y squared would link to circles, but I'm trying to use circles in rectangles. What do I mean by that? So you really need to understand what's going on, like in just your normal Cartesian coordinates, you might think of it as an infinitely thin strip, width of dx, height of dy, right? But x squared plus y squared gives us circles. So really, it is a bit of an awkward situation, but what any other mathematician would say is they would just say switch to polar coordinates, right? So that's all good. That's fine. We'll switch to it, but at the cost of that, we would have to include the Jacobian. So allow me to introduce you to the Jacobian. And before anything, in polar coordinates, we can just write x as r cosine theta and y as r sine theta, right? They will come out to the same thing, because x squared plus y squared will just be r squared cos squared theta plus r squared sine squared theta. And if you pull out the r squared, you'll just get this squared plus this squared, which we all know is just 1. So you will just end up getting r squared. And so this is pretty much going to just make our new integrand e to the minus r squared. That's our new integrand. So a change of coordinates means that we have to change this area element that I was mentioning earlier, which is dx dy, right? So think about what an integral really does, right? So if you have an integral f of x comma y dx dy, you're adding up these infinitely small areas, dx dy, right? But changing the coordinate system that we're working in will alter the shape of these rectangles, right? So that's why we have the Jacobian, right? So in polar coordinates, we have dr and d theta, right? But we can't just write that dx dy is equal to dr d theta. Instead, we have to say it's proportional to, right? And so this is where the Jacobian comes in, right? So we can write dx dy is equal to the Jacobian times dr d theta. Now, if we think about what we're doing here, we're really doing a transformation. Say, like, I don't know, x, just as an example, x comma y would just go to t of u comma v, right? Okay, so this should give us a slight hint. Because we're quite literally altering the nature of space, it would kind of make sense that the Jacobian j is actually a determinant. But why? Because this transformation that I wrote up here actually may scale the area or the volume, right? So really the Jacobian is just measuring how the area of your little element dx dy changes when you shift your rectangles into circles. So our Jacobian is defined, the Jacobian determinant is actually a 2 by 2 matrix of partial derivatives, which is partial x, partial r, and then partial y, partial r, partial x partial theta, and partial y partial theta. And so from those equations I gave you earlier, that x equals r cosine theta and y equals r sine theta, if we compute partial x by partial, let's start with r, then we're just going to get cosine theta, and partial x by partial theta will just be minus r sine theta. And partial y by partial r will just be sine theta. And partial y by partial theta will just be r cosine theta. So our Jacobian determinant will look like this. Cosine theta minus r sine theta and sine theta and r cosine theta, which is incredibly close to the rotation matrix, except we have some r's. So you might see the rotation matrix in a first year linear algebra course or even high school, but yeah. So now we have our Jacobian determinant. If we compute the determinant, we're just going to get AD minus BC, right? That's the determinant of a 2 by 2 matrix. So this times this minus this times this. So r cosine squared theta minus, because we've got 2 minus, we're going to get plus r sine squared theta, right? So if we factor out the r, we're just going to be r bracket then cosine squared plus sine squared, which, as I mentioned from earlier, is just 1. So therefore, our Jacobian, or the factor, is just literally equal to r. And so pretty much from this, we can just write that dx dy is equal to r dr d theta. Nice. Okay, so we're getting somewhere now. So the next step is, let's go back to our original integral, right? Which was I squared was the double integral of e to the negative x squared plus y squared dx dy. And so switching to polar coordinates, right, we make a substitution. X squared plus y squared equals r squared, and dx dy is equal to r dr d theta. And so I squared is equal to times r dr d theta. So the outer integral for theta, we're just going to integrate over the unit circle. So we're going to go from 0 to 2 pi. Oops. And r will just go from 0 to infinity. Not from 0 to r, sorry. 0 to infinity, right? So that's for the inner integral. So let's start by splitting the integral, right? So our first one is just going to be 0 to 2 pi d theta times 0 to infinity, wrong one, of re to the minus r squared dr. Okay, the first one is pretty easy, which is just going to be 2 pi minus 0, right? So you're just going to get theta, you substitute 2 pi for theta minus 0, that's just 2 pi. Nice. So we can write that the integral d theta from 0 to 2 pi is just equal to 2 pi. And how about this other integral over here? So let's take a look at that. So the integral from 0 to infinity of re to the minus r squared dr. Right, okay. Now, this one is actually quite similar to the integral we came across in the video I uploaded of the proof of e equals mc squared, I think, because we had a similar type of integral in the sense that r actually is an antiderivative of e to the minus r squared. And what I mean by that is if you differentiate e to the minus r squared, you get minus 2r times your original function, right? And so we have r to the first power here, and we have r to the first power here. So that's kind of what I mean, right? So from that observation, let's just make an assumption, right? Let's just assume that the integral of re to the minus r squared dr is just equal to e to the minus r squared, right? Therefore, by the fundamental theorem of calculus, if I just go ahead and take the derivative of both sides, then I'm just going to get that the derivative of e to the minus r squared, literally what I wrote earlier, is just minus 2r e to the minus r squared. But I wish to have only a r e to the minus r squared. Therefore, that means that my multiplication factor should be negative 1/2, right? Because negative 1/2 times minus 2 will give me positive 1, because I only want a coefficient of 1. Okay, so what does that mean? That just means that my integral of re to the minus r squared dr will just be minus 1/2 times whatever I originally guessed, plus c. But this was a definite integral, so that would just mean that the integral from 0 to infinity of that is going to be which, in thinking slightly ahead here, it might be more convenient to actually express this in the following way to make the r dependence on the denominator. And why I said that is because now we're gonna actually try compute this. So we should know pretty much from, like, I don't know, high school math, that the limit as x tends to infinity of 1 over x is equal to 0, right? So we have a kind of similar situation going on here, where we have negative 1 over a constant times, a function f of x, right? It actually should be r, but yeah. What we have is that the numerator isn't changing, but the denominator is going to get larger and larger, which means the total value of the expression, call it L, is just going to keep going lower and lower until it hits 0. So therefore, we can say that the limit as r goes to infinity of minus, actually, just for clarity, I will pull out the minus 1/2 because we can do that, times 1 over e to the r squared is just equal to 0, right? Okay, so that first part is 0, and then if we just take a look at the case when we integrate to 0, we're going to get minus 1 over 2e to the 0, which is minus 1/2. Okay, so we're really just going to get that our integral from 0 to infinity of re to the minus r squared dr is just going to be 0 minus 1/2, which is equal to 1/2. Therefore, this integral converges to exactly 1/2. Nice. Okay, so really we've done most of the hard work here. Now we just go back to our original integral, which was I squared equals, I think, the integral from 0 to 2 pi d theta times the integral from 0 to infinity of re to the minus r squared dr. And we know that this part was just equal to 2 pi, right? And we just showed that this part is equal to 1/2. Therefore, I squared will be 2 pi times 1/2, and the 2's will cancel, and we're going to get I squared is equal to pi, which means that I must be equal to plus or minus square root pi, but just for convenience here, I'm just going to write square root of pi. And yeah, so that's really how you do this Gaussian integral, and you get an interesting result. Pi just magically shows up. We initially began with just rectangles and absolutely nothing to do with circles and pi, and somehow ended up with a square root pi in our answer, which is pretty insane. But yeah, thanks for watching.